So here's our final video on section 712 of this systems comprising several loads. So what we figured out was that this 380 volt source delivered 24 kilowatts of active power, but it also at the same time received a net 5 kilovar of reactive power. So the reactive power flows into the local distribution system of the electrical utility company, and it becomes available to create magnetic fields. The magnetic fields can be associated with distribution transformers or transmission lines, or even electromagnetic relays, whatever type of device utilizes the magnetic field to operate. Now, the actual power triangle for this system that we just talked about is represented here. All right. Now that looks a little complicated, but we'll kind of walk through it and see if we can find out all the different parts of it. It's the graphical solution to our problem. And maybe in your physics class, or I can't remember where you would go through this kind of problem. But, you know, when you're adding vectors, you know, that tip to tail kind of thing that you go through, if you remember all that stuff, you know, so I start here. And then I've got 5 kVAR here, right? And I won't step through all of these for you, but you know that would be 5 in this direction, and then I had 2 kilowatts, 2 kilowatts in this direction, right? And then I had 16 kVAR, the purples. The 2 purples are here to here, plus the 9 here, then 8 here, 7 here, 14 here, 8 here, and then I end up, you know, I'm back, and this is my starting point at this stage, and here's my end point here. And then I take that, and let me get a different color, and I create my power triangle. Here's my active component. Here's my reactive component. It's going down since it's primarily capacitive. And then what I do from there is I determine my resultant or hypotenuse from that, and there's my 24.5. And you know, this is a graphical representation of that problem that we just looked at. Then you know we would find, in addition to all these other things that we went through, we could determine what the angle is there. Now, based on a power factor of 0.979, I'll put that in my calculator. Oops, I just picked up my phone. That's not going to do it. I'm going to take my calculator, and I will, from the calculator, I will figure out what that is. Inverse cosine of 0.979, and I get an angle of about 11.76 or approximately 11.8 degrees, and that would be what this angle is here. Okay, so you know this is a graphical representation of what we did, you know, and this is the power vectors that we have added together, which is all that we were doing, you know, in this part of this problem, right? Where we were coming up with all these different parts of this, and this is the graphical solution to that problem. Okay, so again, you know, it's one thing that I come back to about in this text, and having kind of gone through both of these, you know, the idea and the way that this text presents to us these solutions in graphical terms, and you know, at a level of math that's easy to understand, you know, I think we really get a good perspective on what's going on, and I think it aids to our understanding with this. Okay, so I broke this 712 up into 3 videos. Very important section. Let's see, we're going to do probably one more section out of chapter 7, and I think we've got enough of it. And one of them is primarily just qualitative, nothing to work through. And that, I think that will get us there. All right, let me stop this thing. Stop.